Our project involves monitoring and condition assessment of flood control infrastructures and levees. This is a joint venture between Rensselaer Polytechnic Institute and Geocomp. It's a 4-year project funded by NIST Technology Innovation Program, and the investigators are Professors Zengal and Abdul from Civil and Environmental Engineering from RPI, and myself from Electrical Computer and Systems Engineering, as well as Dr. Ellen Marr from Geocomp. So I will give a quick overview of our project. This is a relatively new project. It started in February of this year. I will describe our motivations, goals, and objectives, and then I will describe some of our key technical activities, in particular how we use space-based radar for global monitoring, local sensing strategies, and health assessment, and I'll make some concluding remarks. So I think everyone would agree that integrity of dams and levees is essential for homeland safety. We all know what happened after Katrina. It was a catastrophic disaster. And according to a recent survey done in 2009, the flood control infrastructure in the United States is aging. In fact, the report card for the dams is D, and for levees it's even worse, it's D-. So something needs to be done. So this is a scene from New Orleans during Katrina. There is a levee breach, and we see that it's all flooded. So to see how dramatic this event was, you can look at the picture of New Orleans before Katrina. So this is the same area before Katrina, and this is what happened during Katrina. And if you zoom on some regions, again you see it's mostly flooded, and same happened. Levee breaches occurred outside New Orleans also. In fact, I was surprised to learn that there is a 6,000-kilometer long levee system in the Mississippi region, and these levees are very old. They are as old as 150 years old. It's just a matter of time for these levees to fail. So it's a time-critical problem to monitor and manage the health of these levees. What is being done today is essentially a visual inspection of levees. It's a qualitative assessment. It's done infrequently, sometimes weekly, sometimes monthly, and it focuses on particular components. It has limited capability in terms of understanding the damage and detecting the damage. It's inconclusive in terms of evaluating the health of the levees, and it really cannot predict the health of the levee system. So what do we want to do? This is an illustration of our vision for our project. First, we would like to focus on the entire network of levee systems as opposed to particular components. We would like to monitor the entire levee network of levees. And we also want to pursue an integrated approach in the sense that we would like to use the sensor technology both at global and local scale, combine that with computational modeling, a priori information, and so on, to produce a reliable and simple information to provide to decision makers. So in our vision, we are using a global monitoring system. It's a satellite-based radar system that will essentially monitor a very large area, hundreds of square kilometers, identify vulnerable regions, and those regions will then be instrumented with what we call sensor accelerometer arrays, or my colleagues are working on a new sensor called shape accelerometer for pressure sensors and GPS sensors. GPS will also be a bridge between global and local monitoring. And the information collected from these sensors will be fed into a computational model where some stress strain measurements will come out, combined with some a priori information, and risk and vulnerability analysis will be done. So this is our vision for our project. Now, the project team has 3 sub-teams: Rensselaer Polytechnic Institute, Geocomp Corporation, and we also have a contractor, Measuran. This is a Canadian-based company that works on sensor development. Professor Zegai focuses on the health assessment. Professor Abdul develops field sensors, shape accelerometer for pressure sensing, as well as field monitoring instrumentation. And my expertise is mostly on imaging, in particular for radar remote sensing. Geocomp is involved in field instrumentation as well as data collection, data mining. Daha was a recent RPI graduate. Dr. Daha is also involved in our project. Measurant will be working on sensor design and GPS sensor and sub-sensor designs with Professor Abdul. Okay, so since my area is mostly on radar remote sensing, I'll be focusing mostly on the technical task led by me, two of my graduate students, and I'm also looking for postdocs. So if there are any qualified here, you can see me afterwards. So our objective is to monitor very large areas of Levees systems, usually tens and hundreds of square kilometers, using two techniques, interferometric synthetic aperture radar and polarimetric synthetic aperture radar. The objective is to estimate the deformation of Levees with high accuracy, sub-wavelength accuracy, and perhaps millimeter accuracy, and have a meter per pixel resolution with the available satellite data. We also like to use polarimetric SAR to estimate the near-surface soil moisture content. So here's a quick description of what interferometric SAR is. We have two antennas. We look at the phase difference between the two antennas, and that phase difference is related to the height on the ground. So it's by doing some clever manipulation, mathematical manipulation of the data, we can indeed estimate the surface topography, digital elevation map, as well as subsidence, differential height. So here what we see is a typical interferogram. This is not phase unwrapped. Each fringe corresponds to a certain path length in the loop direction of the radar. So my task is to get the raw data and build these images from satellite data. Now there are a number of challenges in creating accurate interferometric SAR data. They're primarily, we use repeat orbit interferometric SAR systems. Almost all commercial satellites work on that mode. So this results in a number of decorrelations in the phase. This is due to geometric decorrelation, temporal, or there are also some atmospheric effects. Geometric decorrelation meaning the satellite cannot come exactly to the same position the next time when it obtains the data, so that results in some phase contamination. Temporal decorrelation is due to change in the electromagnetic properties of the ground, and this may be due to rain or vegetation growth or scatters moving around. At low frequencies, atmospheric effects are prominent, particularly in C-band and L-band. There is also an issue with the temporal resolution of the data. Right now, for example, we can obtain data at anywhere from 46 days, every 46 days to 8 days with the available satellites. This is not to say that the satellite doesn't go around the Earth. It goes around the Earth several times, but it has to come to the exact same position because Earth is also moving. So that's the reason why it's less. And they're also all repeat orbit interferometric systems. So this is a picture that I pulled out from a Nature article published in 2006. They used radar data, interferometric data obtained from 2002 to 2005, radar sat data. This is prior to Katrina. And they created what's called permanent scatter images from interferograms. So this is the subsidence here is color coded, and each color corresponds to a rate of subsidence change. So the red is higher rate of subsidence. If you look at this area where we have the highest rate of subsidence, that's called the MRGO area, that has the highest rate of subsidence, and there was severe Levee bridges in that area. So you can see that prior to Katrina, there were high rate of subsidence in this area, and these are all in millimeter scale. Okay, so the rate of subsidence in millimeter scale, we can indeed obtain this as long as we have sufficiently large number of measurements. Now, we also like to use polarimetric star data. Polarimetry essentially uses the vector nature of the electromagnetic waves to produce not a scalar value for each point on the ground, but a 2x2 matrix called scattering matrix. And from this matrix, we can extract, for example, material properties of the ground, the shape, etc. And if we combine this with some vegetation models, etc., we can indeed estimate the soil moisture content. Okay, so that's another task that we are pursuing. Oh, 2 minutes. Okay. So these are the radar satellites. All right. Okay, so these are radar satellites available right now. The European Space Agency that has ARS-1, ARS-2 data, and ANDISAT is a C-band satellite system, and it provides data every 35 days. And Canadian Space Agency has radar SAT-1 and SAT-2. We are needing to use radar SAT-2 data. It's a C-band data again, and it provides data every 24 days. Japanese Space Agency has ALOS pulsar. It's a very powerful polarimetric tool. It's an L-band system, and it provides data every 46 days. German Space Agency has TerraStar X. This is an X-band data, so it's a higher resolution, but it has some other issues. And they just recently launched a tandem system, which will provide much better quality data. Italian Space Agency has Cosmos Skynet. This is again an X-band data. So this provides data every 11 days. This provides every 8 days. Now, so what we have done is we have obtained access to various historic SAR data, archives, wrote proposals and so on, Western Hemisphere Interferometric SAR Consortium, etc., Alaska SAR facility. So we have access to all the historic data right now, and we are using some open platform software developed by JPL to reading these data and processing the historic data right now, evaluating the historic data for the New Orleans area and Mississippi Valley. And we are evaluating the technology provided by commercial satellites, and will soon start collecting new data. Now, local field monitoring is led by Professor Tarık Abdun, and essentially, in their previous work, they have developed what's called the shape acceleration array. Now, they would like to add a pore pressure sensor on this array, and also we would like to develop a cost-effective